Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning more about parametric equations, and we're going to find the second derivative of a parametric equation, which sounds like it should be something simple enough. We can already do that with traditional functions. Actually, it's a little bit more complicated than it may seem. All right, so let's get started and we'll see how this all works. So, the derivative of a parametric equation. Now, we did that in the last video, right? The derivative of y with respect to x is equal to dy dt divided by dx dt. Okay, we derived that in the last video. All right, we have two functions, y and x. Both of them are written in terms of t this time, right? And that's why we're finding the derivative of y with respect to t, the derivative of x with respect to t, and dividing them. So let's, for example, say that I had a couple of functions, and we'll find this first derivative just so that we can kind of see what happens with the second derivative. All right, so let's say y was equal to 5t to the 6th plus 3, and x is 4t squared plus t. All right, so if I wanted to find dy dt, well, I certainly could. It wouldn't be too difficult to do. Dy dt is 30t to the 5th. Dx dt would be 8t plus 1. And then dy dx would be dy dt divided by dx dt. So that would be 30t to the 5th over 8t plus 1. That would be my derivative with dy dx would be 30t to the 5th over 8t plus 1. And that would be my first derivative of this parametric set of parametric equations. But the issue is the second derivative is not as simple as it may seem. So what I want to do is I want to find dy dx and take dy dx and find its derivative, right? So I want to find the derivative of dy dx, okay? What I want to find really is d squared y over dx squared, right? Or we could write it like this: the derivative of y with respect to x, its derivative. So what I want to do is I want to find the derivative with respect to x of dy dx, right? Okay, that will give me the second derivative of y with respect to x. But here's the problem. The problem is dy dx, the answer that I have here for the first derivative, is not written in terms of x. To find the derivative of y with respect to x, to find its derivative with respect to x, well, there would need to be x over here in the equation. It's not. Dy dx is written in terms of t, not x. So now what I'm going to have to do then is I'm going to have to find the derivative with respect to t of dy dx. The problem is that's not equal to the derivative with respect to x of dy dx. I mean, look at the two, this equation that you have here. These two are not equal to each other, right? So what I need is what I call a correction factor, okay? I need some kind of correction factor so that I can say I can find the derivative of y with respect to x. I can find the derivative of this thing with respect to t, but then call it the derivative with respect to x. And that correction factor is multiplying by dt dx. So if you look, by doing that, my dt's would cancel out, right? And then I'd be left with the derivative with respect to x of dy dx. Okay? That's what we're going to have to do. Now, how exactly do we go about calculating this? Well, that's actually not as difficult as it might seem. All right? Because the derivative with respect to t of dy dx is easy to calculate. I'm going to derive that. That is the derivative of with respect to t of dy dx. And then I'm going to multiply by dt dx. But instead of multiplying by dt dx, what I'm going to do is I'm going to take dt dx and move it to the denominator. If I take this dt dx and put it in the denominator instead, it flips over and becomes dx dt. So now what I'm going to do is I'm going to find the derivative with respect to t of dy dx. That means derive the top, or derive dy dx with respect to t. Fine, the rules apply to t's. That will be in the numerator. And I'm going to divide this by what I call a correction factor of dx dt. So that's dx dt. That would go in the denominator of what I have here. And that is the correct second derivative with respect to x of dy dx. Okay? All right, so over here, there's another summary of it. So if you're given x is x of t and y is y of t, the second derivative of y with respect to x, again, we just wrote this all out, is equal to this. I'm going to find the derivative of dy dx, okay, in terms of t, and then divide by dx dt as my correction factor. All right? All right, so let's try a couple here real quick. Let's consider these parametric equations. I want you to find the second derivative of y with respect to x. All right, so to find the first derivative of y with respect to x, I have to take dy dt and divide by dx dt. So let's find dx dt, I guess. Dx dt is 2t. Dy dt is e to the t. So now I'm going to take them and divide them. So that's going to be e to the t divided by 2t. So dy dx is e to the t divided by 2t. Okay, now I want to find the derivative of dy dx. So I want to find the second derivative. The second derivative of y with respect to x is dy dx's derivative with respect to t divided by dx dt, which is the correction factor. So I'm going to find the second derivative, or the derivative of e to the t over 2t. So the derivative, dy dx, that derivative, is equal to, I'm going to use the quotient rule. So that's 2t e to the t minus e to the t times 2 over 2t squared. So I can clean this up a little bit, right? There's a bunch of things I can do. I can factor out 2e to the t if I want. It would give me t minus 1 over 4t squared. So this is 2e to the t over t minus 1 over 4t squared. That's the derivative of y with respect to x's derivative with respect to t. And then I'm going to divide that by dx dt. Dx dt is just 2t. So I'm going to put 2t in the denominator here. And now I'll multiply by 1 over 2t. So I can cancel out the 2's if I want. And that's going to give me e to the t times t minus 1 over 4t cubed. And that is the second derivative of y with respect to x, written in terms of t. Okay? So it's a little tricky because you're dividing by that correction factor of dx dt at the end. All right, we'll try one more here. Let's find the concavity for this set of parametric equations at theta equals pi. Okay, so concavity, I need the second derivative for that with respect to x. So let's find the first derivative. So that's going to be dy dt divided by dx dt. We have dx dt is going to be 1 minus cosine theta. Actually, these should be thetas. Right? dy d theta divided by dx d theta. It's not t this time. And then dy d theta, derivative of 1 is 0. Derivative of negative cosine is negative sine. That's going to be sine. Okay, so dy d theta is sine theta. Dx d theta is 1 minus cosine theta. Okay, so now to find the second derivative, it's going to be the derivative of the first derivative over dx d theta, which is the correction factor. So let's find the derivative of the first derivative. So we'll use the quotient rule again. 1 minus cosine, derivative of sine is cosine. Minus, leave the sign there. Derivative of 1 minus cosine is going to be sine. So that's all over 1 minus cosine squared. So that's going to be cosine theta minus cosine squared theta minus sine squared theta all over 1 minus cosine theta squared. Okay, so we have cosine theta minus cosine squared theta minus sine squared theta over 1 minus cosine theta squared all over dx dt. dx dt is 1 minus cosine theta. That's my correction factor. And I can multiply top and bottom by 1 over 1 minus cosine. And that's going to give me cosine theta minus cosine squared theta minus sine squared theta over 1 minus cosine theta cubed. And now I want to find the concavity at theta equals pi. So I want to substitute pi in. Let me erase some of the stuff that I have up here so I have a little bit of room. Or maybe we'll erase this dy dx. We don't need it anymore. We found it. Let's erase this. And let's see what we have here. So the second derivative with respect to x is cosine pi minus cosine squared pi minus sine squared pi over 1 minus cosine pi cubed. Okay, so that's going to be cosine pi is negative 1. And then we're going to have negative 1 squared. Sine of pi is 0. And then cosine pi is negative 1. 1 minus negative 1 is 2 cubed. So that's going to be 1. So 1 minus negative 1 minus 1 is negative 2 over 8. That's less than 0. It's negative. So that means y is concave down. So the concavity at theta equals pi is concave down. And that's the answer. Okay? And that's how you find the second derivative of a parametric equation. As always, thanks for clicking.